Right, so let's see. Here in the following exercises, what we've got are derivatives. But from the derivatives, we should be able to find out where the function is increasing and decreasing. Okay, and then also that will tell us if there's a change in the sign of the first derivative. That will help us locate where are the local max and min values. All right, so what are the critical points? What do? We just set the first derivative to 0, and then you divide the number line again to be able to answer letter B. Plug in test points, check the signs of the first derivative, and then we can decide whether we have a local max or a local min. All right, so let's try number 1. So take the first derivative, which is this one already. It's given. What we're having in exercise 1 through 14 is that even if we don't know the function itself, okay, as long as we know the first derivative, then we can just set it equal to 0, and then there we get the critical values, and then subdivide the number line, and there you have it. You can use the test points. You'll be able to find where it's increasing and decreasing, so that you'll be able to answer letter C. So first we take x times x minus 1 equal to 0. Remember, the derivative is already given, so you don't even have to take the first derivative. It's already given, so all you have to do is just set the first derivative to 0 to get the critical points. So that means what will make the 0 when x is equal to 0, and also when x is equal to 1. Because when x is equal to 0, the whole thing is 0. When x is equal to 1, so these are your critical points. So this will give you critical points. So that answers letter A. Now letter B, at what intervals f is increasing or decreasing? Remember, even if we don't know exactly what the function f is, we do know its derivative, so we would be able to find the intervals on which the function is increasing and decreasing. Okay, so what do we do next? We take test points. So remember, test points are just arbitrary numbers, and I always encircle it. Then let's go ahead and subdivide our section so we can clearly see whether we have a change of signs in the first derivative. So test point to the left of 0, you can use -1. Again, you can use -2, -3, etc. Okay, I just used it because it's convenient. 1/2, and then to the right of 1, you can use, how about 3? 2 is okay, but 3, how? Doesn't matter because these are arbitrary numbers. Now what do? You plug into the derivative, so you have -1. So f prime, we just check -1 times -1 minus 1. So that makes it negative times negative. This becomes positive. So what does that tell us? If it's positive, it's increasing to the left of 0. Now between 0 and 1, so 0 and 1, plug in 1/2, so that's positive, multiplied by 1/2 minus 1 is -1/2, so that's negative. So what would be the product of positive times negative? It's negative. So you have a decreasing function, decreasing on the interval from 0 to 1. So that tells us that we have a 0 slope here. So you see how you've got a mountaintop or a hilltop, which tells us that there's a change in sign of the derivative. So this is a local maximum. Okay, now what about to the right of 3? Well, we plug in 3 times, that's positive, 3 times 3 minus 1, that's also positive. So positive times positive is positive. Okay, so that means you have, again, a 0 slope and positive slope. So that tells us that here you've got a valley. So that tells us that here you've got a local max and a local min. Okay, so let's summarize. For letter B, we say that, all right, where it's decreasing, well, let's start where it's increasing. So it's increasing on the interval. Okay, so we have two intervals from -infinity to where? From minus infinity up to 0. And then another interval would be, where is it positive? The derivative is positive, from 3 to infinity. And then it's decreasing on the interval, okay, from 0 to 1. Okay, so that answers letter C. So those are the intervals that is changing direction. Now it says at what point, if any, does F assume a local max and a local min? Well, since you have a positive to negative, so you go up and then down, that tells us you have a local max occurring, okay, when x is equal to 0. And then from here, you have negative to positive, so you see that you have a local min when x is equal to 1. Okay, so there you have it. We were able to find the critical points by setting first derivative to 0, solving for x. Then you subdivide your number line by, it's divided through the critical numbers, and then you plug in test values, and then that gives you the sign. Plug it into the derivative, and it gives you whether it's positive and negative, and so on and so forth. Okay, and then that will give us the interval on which it's increasing when it's positive slope or positive derivative, and then decreasing means a negative derivative on that interval. And from that, when you have an increasing to decreasing, that gives us a local max, and then from decreasing to increasing, that gives us a local min. Okay, now let's do number 2. So let's do number 2. Set your derivative, which is already given, so we don't have to take the first derivative. When you set that equal to 0, what are the critical numbers? When x is equal to 1, and what makes it 0 when x is equal to negative 2? These are your critical numbers. And go ahead and subdivide your number line into how many sections? There's 2 critical numbers, so you have negative 2 and 1 here. Then we subdivide that into 3 sections. Take a test point. Let's say negative 3 is our test point. Here it's 0, our convenient 0. And then that's 0. It's not a donut, it's 0. And then here, let's plug in 3 or 2. How about 2? Right, so take the first derivative that we have and plug in your test point. So negative 3 minus 1 means that it's negative. You plug that negative 3 here. Negative 3 plus 2 is negative. Multiply the 2 together, you have a positive. So that's the sign of the first derivative. And then plug in 0. In here, that's 0 minus 1 is negative. And then 0 plus 2 is positive. So what's the product? It's going to be negative. And then to the right, you have 2 minus 1. That's positive. Plug in 2 plus 2. That's 4. That's positive. Notice that I don't concern myself with the value. I'm concerned with the sign. So that makes it positive. So you have a change of sign from positive to negative, that tells us, and then a 0, which means you have a local max again. And then from negative to positive means you have a local min at x equal to 1. So letter A gives us the critical numbers. Letter B tells us based on our first derivative test by plugging in test points coming from different intervals, from minus infinity to negative 2, and then from 2 to infinity. This is where it's increasing. Okay, and then on the interval minus 2 to 1, we see that it is decreasing on this interval. So based on what we found here, then we can conclude that a local max occurs, okay, local max occurs at x equal to -2, and then a local min occurs at x equal to 1. And notice that because all we have is the first derivative, we can't locate the critical points. We just know that these are the critical points, but exactly where it is on your, to plot it on your xy plane, we need the original function. But it's okay because still we know that at x equal to -2 there's a local max, at x equal to 1 there's a local min. Alright, here are some more, here in this problem, we do the same thing. We take the critical number. So to get the critical numbers, we set x squared times x minus 1 over x plus 2 equal to 0. And just by observing, as you can see, we see that what makes the numerator first? What makes the numerator 0? Well, you just set x squared times x minus 1 equal to 0, the numerator, and that tells us that x equal to 0 and x equal to 1 is a critical number. These are two critical numbers because it makes the numerator 0. And then the denominator, so that's the numerator, as well as the denominator, x plus 2 equal to 0, means that x equal to -2 is a critical number because why? It makes the derivative undefined. So what you do is whenever there's a denominator, you also set that equal to 0. So when you have a ratio, you take the numerator, set it equal to 0 to get the critical numbers that make the derivative 0, and then you take the numerator, set it equal to 0. That gets a critical number again, and see here it says x is not equal to -2. Remember, because that will make the derivative 0. But does that keep us from testing? No, it doesn't, because the critical points are where it's undefined or where it's 0, where the derivative is undefined or where it's 0. So what's the next step? So, since we've already found the critical numbers or critical points, okay, then we take the real line and we subdivide it. We start from -2, and then we take 0 and then 1. I'll spread it out in this way, okay, and you see that these are our different sections. Take our test points or test numbers, so -3 test, -1 test it, 1/2 test that again, and then 2, say 2. Take the sign of the first derivative by plugging it -3 here. -3, when you square it's still positive. -3 minus 1 is negative. -3 plus 2 is negative, so the whole thing would be positive. So you see that it's increasing, okay, on the interval from minus infinity to -2. What about if we test x equal to -1? Plug it in the derivative, check the sign. So the sign of the first derivative is what? So that's positive because it's squared. So -1 squared makes it positive. Multiplied by -1 minus 1 is still negative. Okay, and then here -1 plus 2 makes it positive. So that tells us that the whole thing is negative. So if it's negative, right? So if it's negative, let me just put that so to make sure that you can see that it's negative, you have a decreasing function from -2 to 0. So what does this tell us about -2? -2 is a local max because you have increasing to decreasing. So it has reached a mountaintop or a hilltop, Then let's try 1/2. 1/2, when you square 1/2, it's still positive. Okay, and then 1/2 minus 1 is still negative. Then 1/2 plus 2 is positive. So this is, in all would be negative. So if it's negative, it's still decreasing. So decreasing to decreasing means there's no extreme value occurring at x equal to 0. What about at right of 1? Let's plug in 2. 2 squared would be positive. 2 minus 1 is positive. 2 plus 2 is 4, that's positive. So the whole thing would be positive, so it's increasing, which means that you have a local minimum occurring at x equal to 1. So let's summarize what we got for the intervals on which the function is increasing. So it's increasing on the interval from where? Wherever you see a slope, a tangent line with positive slope. Okay, so that means it's the interval from, you take it from minus infinity to -2, and where else? Okay, there's your positive and positive, so it's decreasing or it's increasing on this interval as well as 2 to infinity. Okay, and then where is it decreasing? It's decreasing on an interval from -2 to 0, and at the same time from 0 to 2, because it kept on decreasing, and you have a 0 slope and then it's decreasing again. Okay, so these are all the intervals for which the function is increasing and decreasing. And then the last thing we'll have to look at would be local max and local min. So only where there is a change of sign from positive to negative, that means when x is equal to -2, you have a local max. However, at x equal to 0, nothing happens because it was decreasing to the left of 0 and it kept on decreasing to the right of 0. So that's not an extreme value. And then at x equal to 1, we have a change of sign to the left of 1 from negative to positive, which means you have a local min when x is equal to 1.